Okay, good morning, guys. So today we're going to continue with where we left off from the last lesson, right? So our last lesson we talked about turning verbal phrases into algebraic expressions. Today we're going to extend that a little bit into equations as well. So just as a little kind of review here, we'll check out our do now. So the first one says the sum of twice a number and -7. So we're going to say I know that sum means addition. I know twice a number means 2x or 2n or 2 times whatever your variable is. So I want the sum of this number and -7. So at this point in the lesson, guys, I would ask, in person, I'd say, well, what's a better way of saying 2x plus -7? And of course, the better way is just saying 2x minus 7. But either one is going to be appropriate. For the second one, 18 more than half a number. So one way we can do it is we can say half x plus 18. And of course, we can represent the half x as x halves, which we talked about in the last lesson. And we can also use a decimal representation, right? We could say 5/10 x plus 18, right? All different ways of representing the same expression. Number 3, right? We've got less than a number. So when we see less than a number, we know we have to subtract from the expression. So we're going to say that I first have to take 3/5 of a number, which we can call that 3/5 x. And now if we want 12 less than that, we have to subtract the 12 from it. Again, this less than is very tricky because we have to switch the order of the expressions. So it's 12 less than something, we have to subtract 12 from it. So 3/5 x minus 12. Number 4 is a bit more straightforward. 10 times the sum of 7 and a number. So we have to do a few things here, right? What am I multiplying 10 by? The sum of 7 and a number. So how do I say the sum of 7 and a number? 7 plus x or x plus 7. How do I take 10 times that? You have to put the 10 outside and we have to use parentheses. So we do have to be very careful with that one. 5 and 6, hopefully we remember what we did with our percents. We said if there was a percent more, we would add it to 100% and convert to a decimal. If it was a percent less, we would subtract it from 100% and convert that to a decimal. So 11% more than my number, right? My number being 100% of my number is now 111% of my number, which is 1.11x, or 111% of x. Now 95% less. Well, if I've got 95% less, I've only got 5%. Now 5% as a decimal is 5/100ths of x. And 7 is kind of a little extra, kind of a challenge. So it says the product of 3 and a number, comma. Now we don't generally care too much about punctuation in math, but here it is actually going to be really significant because then it says squared. So in other words, you got to take this whole thing, and whatever that is, we're going to square it. Okay, the product of 3 and a number, so that's 3x, squared. Well, what happens if I do this? Well, that's x squared times 3. That's incorrect. I need to take the product of 3 and the number, which is 3 times x, and I need to square it. I need to put parentheses and then put the exponent of 2 outside. That's something we'll tackle a little bit more when we start talking about order of operations pretty soon. All right, now, usually I have the first thing I ask when I say, all right, guys, well, this looks pretty similar to what we did previously. What's different, right? What word do we see here that we didn't see previously? And of course, that word is. And is our clue that we have an equation, not an expression. So we're going to say, all right, well, this is 19. So I know part of this is going to be equals 19. Now, what equals 19? 8 less than 3 times a number. So we're seeing all those little things that we saw previously. 3 times a number, right? How do I say 8 less than that? Well, I have to subtract 8 from it. All right, so 3x minus 8 equals 19. Let's look at the second one. 10 more than twice a number is, right? So there's my equal sign. Or even is equal to, that's even more of a giveaway, 3 times that same number. All right, let's deal with the first part. 10 more than twice a number, okay? 10 plus 2x, or 2x plus 10, is equal to 3 times that same number. Okay? Now, the next thing I would generally do in class is I would have to ask the question, what if it said 3 times a different number? Well, if it was 3 times a different number, we'd have to use a different variable. So 3y or 3a or 3c or something like that. Okay, but 10 more than twice the number, 10 plus 2x, is equals 3 times that same number, 3x. All right, so why don't you guys try these two on your own before we move on to something new. So you can pause it, work on them in your notebooks, and then we're back. 6 more than twice a number is 24. Right? What's twice a number? 2x. What's 6 more than that? Plus 6. Right? So we don't really care if it's 6 plus 2x or 2x plus 6. Technically, I guess it would be a little bit better to say 6 plus 2x, but mathematically it really makes no difference when we're talking about a sum or a product. For the next one, 10 less than 4 times a number is 18. And again, we see that less than a number, so we know we're going to switch the order of these terms. So we have 10 less than 4 times a number, right? So 4 times a number is 4x. 10 less than that means we subtract 10. So 4x minus 10 is equal to 18. All right, now we're going to start writing equations from verbal phrases that don't have a variable defined. So when we see this, right, define variables. Define variables means write a let statement, right? In other words, if I say 3x plus y equals 15, someone's going to look at this and say x, y, what do those things represent, right? So it's really important that we write a let statement. So it says, what is the total cost of buying several shirts that cost $15 each? So there's two things that are variable, that are changing, right? The obvious one is the number of shirts, right? It says several, so that's obviously implies that that's a variable. And the second one is our total cost, which the total cost is going to change based on how many shirts we buy. So I'm going to write a let statement that's going to say, let T represent the total cost and I'm going to write a second one that says, let S represent the number of shirts. So now let's see what equation we can write. So it says, what's the total cost of buying several shirts that cost $15 each? So I would say, well, the total cost of my purchase is going to be the number of shirts I buy times $15. So T is equal to 15S. Right? What's the total cost of 3 shirts? I would substitute 3 for S. 15 times 3 is 45 is my total cost. What's the cost of 10 shirts? Right? Same thing, sub in 10 for S. Someone could say, well, if you spent $90, how many shirts did you buy? Well, now you'd substitute 90 for T. You divide both sides by 15, you get S is equal to 6. So when we see defined variables, that's what we're talking about. All right, this one's requires a little more thinking, maybe some things that we haven't necessarily seen yet, and that's okay. But we're going to focus on defining the variables. So we have a table here that is showing the total cost of a purchase based on the number of pencils. So I'm going to be consistent. I'm going to say, let T represent the total cost. And we're going to say, let P represent the number of pencils. But now they don't actually tell us anything, right? Here they told us the shirts were $15 each. We knew that was going to be our coefficient. Here we don't have that. We have to actually figure it out, which isn't too hard, right? If 4 pencils is $1.20, we can say $1.20 divided by 4 gives me 30 cents. What about if I bought 6 pencils? Well, that would be $1.80. And that would work for all of them, right? This is what's called a function rule. Some people call it an input-output rule. We can figure out that using all of these, and it would have to be true for all of them, and that's something we'll revisit in a few months, each pencil is 30 cents. So based on my let statement, I can write a really simple equation. The total cost of my purchase is that, right? I really should be using lowercase letters, so it doesn't really make a huge difference. The total cost T is equal to 30 cents per P. So if I was to substitute 4 for P, it would give me $1.20 for T, and so on. All right, so here's another now try. So this one's a little bit more sophisticated than the other one, so I want you guys to pause it and try it on your own. And now we'll take a look at it. So let's define the variables, right? So once again, we have the total cost of buying a pair of jeans, right? A means one. That is not going to be a variable statement. Several. How many hats did we buy? I don't know. Several. That's going to be our variable. So I'm going to say let T represent the total cost. And we don't have to do anything about jeans because, again, we know we're buying one pair of jeans. That's not a variable. That's fixed. That's defined. That's a constant. And I can say let H. And again, it doesn't matter what variables we use. So I'm going to do this one differently now that I just thought of it. I'm going to use X and Y. And I'm even going to switch it. Generally, Y is what we call our dependent variable, and X is our independent, right? The value of Y depends on the value of X. So in this case, the total cost depends on how many hats we buy, but if you did it the other way around, it's okay. This is going to represent the number of hats purchased. So let's talk about my equation here, right? My total cost, in this case Y, is equal to what? Well, I bought a pair of jeans for $40. Plus, I bought some hats. I bought X hats for $20 each. So that's what your equation is going to look like here, okay? Your total cost Y is equal to the, and if you wanted to put a 1 being multiplied by the 40, you can do that, though obviously it's not necessary. So Y is equal to 40 plus 20X, right? The $40 pair of jeans plus X hats that cost $20 each. All right, guys, so this is your homework. So you're going to, for each of these defined variables, you do not have to copy the questions. But what I want to see is I want to see this for each of them. There's only 3 of them. So just to get you started on the first one, right? What is the total cost of buying a sweater for $30 and several shirts that cost $12 each? That's very similar to the one we just did. You can say let's C or X or Y, whatever. Let's say let C represent the total cost. Let's say let S represent the number of shirts purchased. And then your equation would be C is equal to 30 plus 12C. So I just did the first one for you. But again, guys, for each of these, I want to see the let statements. There should be 2 of them. And then the equation itself. And then you don't have to do anything as far as solving it. In some cases, you may be able to. In some cases, you may not be able to. Like for number 3, perhaps. But you don't need to solve the equations. We haven't done that yet. Okay, so again, 2 let statements and an equation for each of these. As always, any questions, we talk about it on Google Classroom.